Hi, today we are going to see about protein binding. We'll see what are the effects of the protein binding and also we'll see the kinetics of the protein binding. So what is protein binding? Any drug which is going to, if you give a drug, the drug is going to bind to the protein which is present in the body or which is present in the blood. That bounded protein, that bounded drug to the protein will have some effects. It may be advantageous or it may be disadvantageous. We'll see what are those effects. If the drug is bounded to the protein, the amount of drug which is available for the action at the site of action is very less. So in this case, it is disadvantage for us if the protein binding is more for the drug. One. Next, if the protein binding is more, the clearance of the drug also will be affected. Because the drug is not in free form, the drug will not be cleared through the kidney. So the clearance of the drug also will get affected. Dose adjustments of the drug also will get affected. And also the protein bounded drug will have more half-life compared to the normal drug, because normal drug will get cleared through the, what happens when you inject the drug into the body, it will go to the blood. This drug will show action. After showing the action, it will go to the kidney. First, it will go to the liver, metabolize, go to the kidney, then it will get eliminated. This is for the free drug. If the drug is bounded to the protein, when it enters to the blood, if it bonds to the protein, drug is bounded to the protein, then what happens? The drug is not available for the liver to get metabolized. The drug is not available for the liver to get metabolized. Obviously, the drug will not be available for the kidney to excrete. This is the reason the drug will stay there for more time within the body. In turn, it shows sustained release action of the drug. It is advantageous. Okay, it is showing sustained release, but the amount of drug which is available at the site of action will be less. To know how the drug, to which proteins the drug will go and bind, those are albumin, globulin, lipoprotein, and glycoproteins. In this, these are the proteins which it will go and bind. In albumin, again we have four sites for the drug protein binding: warfarin, benzodiazepine, etc. We have four types of sites for the albumin for the drug to bind. What I am saying is, if this is the albumin, it has 1, 2, 3, and 4 sites. Site 1, site 2, site 3, site 4 for the protein to bind. Means it can bind 4 protein at a time, albumin. So this next we want to know what is the kinetics. So how much strong it is binding. What is the um, binding force, and with how much strong that protein is binding, and also what are the number of binding sites for the drug. We want to determine this. There are number of binding sites for the drug and what is the strength of that binding. We want to know. For that, we need to study about kinetics of the protein. Now we will see how to derive the equation for the kinetics of the protein and how to conduct the experiment for the protein binding. With the kinetics of the protein, we have, let's say, assume I have protein which is unbound and drug going to form a complex, that is drug protein complex. This is the reaction between drug and a protein. Drug comes, reacts to the protein and forms drug protein complex. If I apply law of mass action and stability for this, we'll get K is the constant, stability constant of the complex is concentration of product divided by concentration of reactants. It's the product of concentration of reactants. Now, what I want, the main problem where you are going to struck here in the kinetics is you don't know what to derive. So, to make it simple, we have to consider something in the mind. That is, I want to know how much bounded protein is available per total protein. I want to know what is the fraction of bonding. This is what I am representing. What is the fraction of binding bounded protein to the total protein? See how much protein is available bounded to the drug divided by total amount protein, means fraction of protein bounded. Okay. For this, I need this part in the equation because I am going to draw a graph between fraction of protein bounded to amount of drug available. It looks like, see, amount of gas adsorbed per unit mass of adsorbent and pressure. Amount of gas adsorbed per unit mass of adsorbent and pressure. What it is? It is of Langmuir. So if you assume that protein bonding to the drug is a type of adsorption, so we want this type of graph to be drawn. To draw this type of graph, I am going to derive the equation for this. So I want this thing on the y-axis, I want this thing on the x-axis. We will see how to derive that. Further, take this side. So what we will get? Concentration of protein multiplied by concentration of drug and the constant, that is stability constant of the protein multiplied by concentration of drug protein. Now see what I want. I want the fraction, but total protein is not there. This PT means total protein. Here I want PT. PT means total protein. Total protein is not there here. So I want to incorporate the total protein here. Further, what I will do? We know that total protein is bounded protein. Concentration of total protein is concentration of bounded protein plus concentration of free protein. Total protein is what? It is the summation of bounded protein and free protein. Rearrange the equation, you will get minus free protein. Now assume this is the equation 2, assume this is the equation 1, substitute 2 in 1. So what you will get? In place of free protein, I have to substitute this. What I will get here? Here I am substituting this equation, so we will get Pt minus Ep concentration whole multiplied by concentration of D and multiplied by K is equal to remaining as Tp. Multiply this with this part, you multiply with this two. What you will get? Total protein multiplied by drug and stability constant minus bounded protein multiplied by drug and stability constant is equal to P. So what I want this ratio on y-axis. So I want that to be on y-axis. So what I will do? Take this part this side, because we have dp here, bounded protein here. Take this part this side. What will we get? Concentration of total protein and concentration of drug, the stability constant. This part is going that side, so it will plus dp concentration d and k. Now here we have dp and dp in common, that is bounded protein as a common term. Take out that. What will you get? I will write this equation once again there. Total protein concentration, drug concentration, stability constant is equal to bounded protein plus drug plus stability constant. Bp is the common here, take it out. What will you get? In case dp, if I take out as a common, get 1 plus d and k. So what I said, I want the fraction. Fraction is what? Bounded protein to the total protein. I want this here, I want this here. So rearrange the equation. Send this side and pt this side. What will you get? D k, because pt went that side. Remaining is 1 plus drug concentration K is equal to, you will get dP divided by dt concentration, bounded drug and unbounded drug. Again here, take this common. What will you get? Drug concentration and K divided by 1 plus drug concentration and K divided by drug concentration and K, which will get cancelled. I am taking this for the common for both things. It will get cancelled. This is d bounded protein by fraction T concentration. So what is remaining here? Remaining is drug concentration, stability constant divided by 1 plus 1 is equal to by Kg concentration. Okay, what we are seeing here, this is the concentration, this is the fraction of protein bounded. Okay, so how it looks, y, I want to draw a graph, we'll draw a graph. It looks like which is there. I will give this link in the description as well as card, icon. Okay, y, convert this equation into graphical form. How? Y is equal to mx. So y, m is slope, x is this. You can ask me, sir, why you are taking m as k? X, see, I know how much drug I am giving. I don't know what is the fraction of drug which is going to bound to the protein. Okay, I don't know how much protein is going to bond, but I know the drug, so I am keeping this as the x-axis. What you will get? You will get a graph something like this. This will be the y-axis, E by dt. And what is x-axis? Drug concentration. As the slope is positive, you will get a positive slope. Sorry, here you won't get a straight line. It is absorption, so you will get something like this. What it shows? As you increase the drug concentration, there will be saturation of the protein by the drug and there will be no further complex formed by the drug to the protein. There is no protein binding occur further. See, initially, if you increase the amount of drug concentration on the x-axis, your fraction of drug bounded protein also increases. Fraction of bounded protein to the drug also increases, but at particular level it get level of indicating it is being saturated. All sites in the protein is being saturated by the drug. It is same as adsorption. Okay. Now the problem here is in this equation on the graph, I can't determine what is stability constant K, and I want to know how many number of sites are available for the drug. The drug may attach to 3 and 4 sites. I don't know that. So how many number of sites are available, and also I want to know what is the stability constant. From this graph I can't get that. Further, again we are going to modify the equation. This equation we are going to modify it and we are going to derive another equation. This part I will write separately. Yeah. In the previous equation and in the graph, we can't determine what is the stability constant K value and N value. For that, we slightly modify this equation. What we will do is assume this fraction of protein bounded as R. Assume this as R, some value. So what will you get? R is equal to K into the concentration divided by 1 plus K into the concentration. Now reciprocal it. Inverse the equation, reciprocate the equation, turn the equation upside down. What you will get? 1 by R is equal to 1 plus Kd divided by K into T, that bounded concentration. Now I want to plot a graph for this. So just take this Kd common for both. What will you get? 1 by R is equal to 1 by drop concentration plus Kd by K, which will get cancelled. So what is left out here is 1 by R is equal to 1 by K into dV plus 1. Okay. Now draw the graph for this. What will you get? This is Y, this one is M, and this one is X. So what will you get? If you draw the graph, you get 1 by R. That is, R is the fraction of protein bounded by R. 1 by, see this is 1 by D. X-axis is 1 by drug concentration. The slope is positive. You get the positive graph. Okay, and the slope will be 1 by K. From this graph, we are going to determine a stability constant K. I want to know how many sites does the drug have. Simply, you multiply this equation to know how many sites does the drug have for the complexation to the protein. Now assume N is number of site of complex or number of sites for binding of the drug to the protein. Assume it has N. So I want to know how many sites that the drug will be going and binding to one protein. To determine this, just multiply this value to this equation, you will get 1 by r is equal to 1 by n multiply 1 by n here. So 1 by n, what will you get? K and d plus 1 by n. N is the number of sites. Okay, number of sites for complex and number of sites for absorption and number of sites for binding. Okay, binding. So if I want to plot a graph for this, how will you get? Same simple graph, that is 1 by r, 1 by d will be on the x-axis, positive slope, and this intercept will give 1 by n, number of sites binding, and the slope will give you 1 by n k.
This equation looks like Langmuir adsorption equation. You can see the straight line. In textbooks, it has given as the not this equation. Previous equation has been given as Langmuir. A previous one is Freundlich and this one is Langmuir. Just check in the textbooks. You can know what is wrong there. Okay. And to say this is only my assumption.
Graph. This is called as Cole's double reciprocal equation, and this is called as graph. What is the use of this? Through this graph, you can determine number of binding sites and also number of what is the stability constant for this. But there is a problem. What is the problem? This whole equation graph will get straight line only when drug concentration. You get the straight line for this equation, Cole's reciprocal graph equation, only when the drug concentration is less. Or if the drug concentration is very minute, then only you will get straight line for this. So what should I do if I have more drug concentration? For the drug whose dose is less, you can use this one. If the dose is more, if the drug concentration is more at the site of binding, what will you do? For that we have another equation. So we will see how to get that another equation. Yeah, we'll see the rearrangement of this equation. Previously, in this equation, you can't get n value and k value when the concentration of the drug is high. To get that value of n, number of sites available, and value of k, stability constant of the protein bounded to the drug, for that you need different equation. In higher drug concentrations, you need different equation. For that, we will modify this equation. How we have to modify this? Just keep in mind, I want fraction of drug protein bounded by drug concentration on y-axis and fraction on x-axis. To get this, we want to modify this equation in y is equal to mx plus c. This is y and this is x. So to get that, we'll modify this equation. First, we'll see 1 by r is equal to, take n, k and d as common. What will you get? By n, k and d. If you take common, what you will get? You will get 1 by nkd. You will get 1 plus kd. Okay. To get this equation, I just take nkd as a common outside. Now, if you multiply this again, you will get same equation. See, if you multiply here, you will get 1 by nkd, and also here you will get kd by nkd. Kd will get cancelled. Here will be remaining here. So this equation is correct. Now send this here and send this here. You will get n k, drug concentration is equal to r into 1 plus k d. Multiply this r to this, you will get n k drug concentration. Wherever I am writing d, it is the concentration of drug. Okay, is equal to r plus r k drug concentration. What I said, I want r by d. So how to do that? I want d here. So to get d here, where is d? Here and here. So take this side and take d common. What will you get? N k d minus r k d is equal to r. So d is common. Take out dm. N k d minus k d is sorry. If you are taking d out, sorry. Okay. Take this d common. Then what will you get? N k minus r k is equal to, not is equal to, sorry, n k minus r k whole, d is common here, is equal to r. Send this d there, you get r by d is equal to n k minus r k. Now we will see, this is y, y-axis r by d, r by d is there, x-axis is r, so this is x, this k will be your slope, and remaining this one will be c, intercept. As we have negative here, we'll get negative graph. I'll draw the graph here, get negative graph. As we have negative slope here, we'll get the negative graph. The graph will be like this, something like this. Now, if the graph curves here, just extrapolate the straight line until it touches this. Okay. So this will be your n and k. Okay. In this straight line, we'll get the slope that is 1 by. You'll get the straight that is k. Okay. In this straight line, slope will give k value, that is stability constant, and the intercept will give number of sites available and stability constant. Simple. Now you can determine number of sites available and stability constant in higher drug concentration by this equation. I will write this equation once again, that is r by d is equal to n k minus r k. This equation we call as Scatchard plot. This plot we call it as Scatchard plot, and the use of this plot is, this has some limitation, that is, if you have you can determine the number of sites available and stability constant only when the binding site is of same class. Just as said you before, protein will have 4 binding sites: diazepam binding site, etc., etc. That binding site, the drug which is going to bind to that site will be same class, means all the drugs should bind only to the diazepam site, then only this equation is valid. Okay, then only this equation is valid. By taking this equation, you can determine what is the number of binding sites and what is k value on higher drug concentration. So previously you should know which type of protein you are going to take, because you should, the binding site should be common for all. To conduct this experiment, you should know which type of protein you are going to take. The nature of protein and nature of drug should be known here to conduct this experiment. Remember, the nature of protein and nature of drug should be known here, because it is asking, it is saying the n value will be for same class of binding site. Drug should bind, all drugs should bind to the diazepam site only. For example, diazepam site, then only you can conduct this experiment. What happens if I don't know? If I don't know the protein, if I don't know the nature of protein, how the equation will change? Yeah, if I don't know the nature of protein, then this equation will change like this. In this equation, if you plot a graph, you will get a negative slope. Slope is negative here. So on y-axis, you take the ratio of dB, means drug bounded to free drug. Ratio of drug bounded to free drug, and this pt means total protein. So you can determine, number of sites as well as stability constant through this. How? Through the slope you will get stability constant, and through the intercept you will get number of sites. And this, in case where you don't know the nature of protein, in that case the equation will change like this. How the graph looks, just see here, same, nothing. On the y-axis you have this one, and x-axis you have dB, means bounded drug. Okay, this one, slope is negative, you get a negative slope. Slope will give minus k, this one, and the intercept will give n, k, and the concentration of total protein. Together you will get the n, k, and concentration of total protein. This is how the graph will look for this. And this finishes the kinetics of protein. Hope you understood. Thank you.